Now look at some of Chapter 13 problems that will be useful to consider. Starting with number 9. Now, number 9 says this. We have this reaction in which looks like I have a white pen that doesn't work so well to write on white paper. Here we go. We have this reaction in which water combines with carbon monoxide to produce carbon dioxide and hydrogen gas. Now keep in mind, this is a reversible reaction. So in addition to the forward reaction, the reverse reaction also occurs. So this system is put at equilibrium, and then we insert carbon monoxide. But the thing about this carbon monoxide is right here. Carbon 14 is a radioactive isotope of carbon. So we put that in here in the question. We put that in here with the carbon monoxide. And the question, let me find that question in my book here, number 9. The question is, will the carbon 14 be found only in carbon monoxide molecules? Is that the only place you will find it? Or will you also eventually find carbon 14 here in the carbon dioxide molecules? Well, the answer, most of you decided, was that if this is indeed a dynamic equilibrium, some of this carbon monoxide that it has carbon 14 in it will react with the forward reaction, and you'll get carbon dioxide with carbon 14 in it as well. So that's the part you need to be sure you describe. Down here, write the answer. You can't just write what I've got here on the screen. You've got to write the answer. Number 10 describes 2 different experiments. One, where you're starting with 1 mole of water and 1 mole of carbon monoxide, and the other starting with 1 mole of CO2 and 1 mole of hydrogen. And here they say, at equilibrium, when it's reached, will there be any difference between experiment 1 and experiment 2? What do you think? I am going to let you decide on the answer to that question. Question 13. Explain the difference between Kc, Kp, and Q. So I think it's important for you to look at that, but I think you can find that very easily. Just keep in mind the name of this if you need to look it up and see what is this Q thing. It is called the reaction quotient. Oh boy. There we go. Now, the reaction quotient, that's what you can look it up if you need to know more about this. Of course, this is the equilibrium constant. If you need to look that up, now the only difference here is this is the equilibrium constant in terms of pressure. Also just called Kp. So look those up, see a little bit more about them. Number 16, which of these statements are true? We've discussed this a bit in class by now, but there are 5 statements here. And notice they can only be true if they are always true. A lot of these are true some of the time, but question A is actually false for solids or false for pure liquids like mercury or bromine or things like that, even pure liquids like benzene or liquid water even, because the equilibrium system only is for solutions or gases in chemical reactions. B, when B is added, equilibrium constant will raise. Oh, that's false. K is constant, remember? It's constant as long as the temperature remains constant. So definitely a false. The concentrations will adjust, the system will come to equilibrium, and K will still be K. C, when the temperature rises, K will also rise. Well, that's true for exothermic reactions, that you'll end up pushing the system more towards products. But if it's endothermic, when you raise the temperature, actually K will drop, so it's not true all of the time. D, when the volume of a system is increased, equilibrium will shift to the left. That is false for reactions where there's more than 1 mole of reactants, more than 1 mole on the left, because when you increase the pressure of that system, we're talking about a gas system here, it would actually push the system to the right. So D is not true all of the time. E is the only one that's true all of the time. Now number 17, you need to write the equilibrium expression for each of those. I've put the example here for C. Of course, for all of these, remember, pause the video and take a closer look if you need to. 18 is the same as 17, except you're writing these in terms of the partial pressures in the system. So write the equilibrium expression for each of these as well. For number 19, we go back to the lecture we looked at earlier that says if we take an equation and we rearrange it, we can calculate the new K just by based on the old K. So in part A here, we are multiplying by a coefficient of 1/2. So we take the original K and we raise it to the 1/2 power. Now be sure you calculate that. Don't just leave it blank, or don't just stop. Don't just stop with this part here. No, we need to go on and calculate it and find this answer. Be sure you do that here for number 19. And you can check the answers in the back of your book if you want, but it would be a really good idea to calculate these. B, you'll see that in B, from this reaction up here, we're simply reversing the reaction. That's all we're doing. So the new value for K is 1 over the old value for K. So be sure you calculate that. In C, if we're going from the original equation down to C, you see the thing we're doing is we're reversing the reaction, but we're also multiplying by 1/2. So the new value for K is 1 over K raised to the 1/2 power. And be sure you calculate that. In D, we have the forward reaction, but we're multiplying through by, let's see, a factor of 2, it appears. So the new value for K is just the old value for K squared. So that's 1.3 times 10 to the negative 2 squared. And be sure you calculate that answer. Number 20, you work the same way. Here's some hints if you need some help.